Hello and welcome. Today we're doing a question from LeetCode called remove nth node from end of list. It is a medium. We're going to jump right into it. Given the head of a linked list, remove the nth node from the end of the list and return its head. Example 1, we have 1, 2, 3, 4, 5 as our input linked list and n equals 2. So we want to remove the second to last element, which is 4. So our output linked list has a head at 1, which points to 2, which points to 3, which then directly points to 5. There's no 4 in there. Example 2, we have a linked list of just 1, and we want to remove the very last element, which is also the first, so we output nothing. We've removed our entire node, and so there is no linked list anymore. Now, this is an edge case we want to keep in mind while coding up. And example 3, we have 1, 2, and we want to remove the very last node once again, so we would just output node 1. Now we have some constraints and a follow-up. Could you do this in one pass? Yes, let's do this in one pass, but before doing so, let's take a step back and sort of recap exactly what a linked list is. So what is a linked list? It is made up of nodes where each node has exactly 2 pieces of information. We have our current value and the pointer to the next node. And that is it, right? So we have no other information. If I was dropped randomly in the middle of a singly linked list, all I would know is my own value and the node directly in front of me. I would have no idea how many nodes are behind me or are ahead of me. So how would I even remove nth from the end if I don't know where the end is or nth from the end is? Well, one way to approach this would be to do it in 2 passes. I would go through my entire linked list and count up how many nodes there are till I hit the end. Then I would go through it again, stopping at n minus whatever that length was, and remove that node. So how would node removal look like? Well, that's easy. All that is pointer manipulation. Say I had the following example. This is a linked list from example 1, except n equals 3 this time. So that means I want to remove third from the end, which is node 3. Node 3 right now is in the linked list because 2 points to it, and then 3 points to the rest of the nodes. So what if we just excluded it entirely? What if instead 2 pointed directly to 4? That's exactly what a node removal is. We're going to have 2's next value be its current next. So this is what it would look like. 2's next, instead of pointing to its current next, points to its next, so it points directly to 4. We now have a linked list where head is 1, which points to 2, which points to 4, which then points to 5, and then none. So 3 is not included in this linked list. Now, if we wanted to do this in one pass, how would that look like? A way to do that is to make use of 2 pointers. So we're going to have pointer 1, pointer 2, and we're going to have the distance between them be n. They're going to increment at the same time, and once that first pointer hits the end, our second pointer is going to be n from the end, right? So if I had p1 and p2, and the distance between them was n, so this is 3 over here, right? 1, 2, 3. Well, now once I start moving this down and once P1 hits the end, it's none. There's no node in the linked list anymore. P2 is at the node we want to remove. So that's what we're going to do. We're going to start off 2 pointers from the beginning of our list. And once we increment P1 n times, or actually greater than n times, because we want P2 to be at the node right before the one we want to remove. That way we can just change our pointers, right? So once P1 is greater than a distance of n, we've passed more than n nodes, we're going to start our P2 pointer. And then once P1 is at none, all we have to do is some removal. So to code this up, we are going to have P1 and P2 start at the beginning, both here, so at head. So P1 equals head and P2 equals head. Now we want to keep track of how far P1 goes, so I'm going to keep counts, initializing that to 0. So while P1 not equal to none, it is still traversing nodes in this linked list, we are going to make it move forward. So P1 equals P1.next, and we're going to increment its counts. So counts plus equals 1. And once count has gone past n, I want to start incrementing P2. And I want to do this before I even increase the counts for P1, so it's going to be up here. So if counts greater than n, P2 equals P2.next. So now we are moving P2. Once this while loop ends, once P1 is at none, P2 is going to be right before the node we want to remove. After that, all we have to do is the node removal. So P2.next is going to equal P2.next.next. So P2's next is now its next value. It's going to go directly to 4, and all we have to do is return head. So I'm going to comment this out, and then we can go ahead and run this code. So I'm going to go ahead and run code. It is accepted, and now when I submit, I get a wrong answer. Now let's take a look at this. So our test case is 1 and 1, which means we have just one node, and we want to remove the very last node. Let's see what we get. We get none type object has no attribute next. So remember what we talked about earlier. There is an edge case that we want to keep in mind, and I'm going to be going through this because I think while it's very important we are able to code things up correctly, it's arguably even more important to debug and figure out how to fix it. So now that we have run into this error, let's just go through this example step by step, right? I have a linked list where node is 1, which then points to none, and I want to return a linked list with the last node removed. So I need to be returning none. Right now, P1 and P2 are both here. Counts are 0. While P1 is not equivalent to none, I increment P1 up by 1. And now it is none. So now when I want to return P2's next, there's really nothing to work with because its next is none, and none has no next attribute, right? So how can we fix this? An easy fix for this is actually creating a dummy node in the very beginning of our linked list that points to our head. So what I'm going to do is I'm going to create a dummy node. This is going to be a dummy list node. So right over here, the value is just going to be 0, and the next node is going to be our head. So essentially we're going to have dummy and then 1 and then none. So P1 can still point to 1, but P2 is now going to point to dummy. And now we want this distance to be exactly n, not greater than n, since they're already 1 apart. So I'm just going to move this if condition down over here. So now when we go through this, right, while P1 is not equal to none, we do P1.next, so it is over here, and count is 1. Now n was also 1, but we're not greater than 1, so we don't increment P2 at all, and it stays where it is. So now once we are out of this while loop, because P1 is now none, P2.next equals P2.next.next. So the next of the dummy is actually none. So there is no node here. It's now going from dummy straight to none, and we would return dummy.next. There's no head anymore because that would just be 1. So now we want to return dummy.next, which is none. So this is only to address that case where we don't have that first node anymore. Otherwise, this would work perfectly on all the other use cases, and we will actually go through run an example. First, let's just go ahead and run this code. So now it is accepted. So now when we go and submit, it is accepted as well. Now before leaving, let's just run through a super quick example. Let's say we had 1, 2, 3, none, and n was equal to 1. So we want to remove this very last node. What would that look like? Well, let's just go line by line and see how our code is going to run. We are going to have a dummy node. This is going to have value 0, and it's going to point to our head. So just to rewrite this, we are going from 0 to 1 to 2 to 3, and this is just our dummy node 0. P1 equals head, so P1 is over here, and P2 is at the dummy over here. Counts equals 0. While P1 is not equal to none, it is not. P1 equals P1.next, and counts equals counts plus equal 1. Counts is not greater than 1, so we don't increment P2 yet, and we are back in this while loop, so we increment P1 again, increase counts. It is now greater than 1, so we can move P2 up as well. Back in the while loop, P1 is moving up 1, counts is 3, and we move this down as well. Now we hit this condition, P1 is none, so we can't continue in our while loop, and P2's next equals P2's next. So essentially, this is going to look something like this. And all we have to do is return dummy.next. So dummy.next, so we're going to return node 1, which points to node 2, which points to none. So that is our linked list with the nth value removed. Now, before leaving, let's actually also quickly run through the recursive approach for this very same problem. Okay, how do we do this recursively? It's not that much different than what we just did. We want to implement the same logic, right? We want to find the node that is n plus 1 from the end, so that way we can just change pointers. But this is recursion, and this is a singly linked list. So say we go all the way down our linked list at the very end, we have no way of going back, right? There's no connection in the linked list where we can go back and see where n or n plus 1 is. So what we're going to do is recursively go down our entire linked list. Once we hit none, once we're at the very bottom, we're going to go right back up our recursive call stack up until we go n plus 1 levels or indices or counts high. At that point, all we have to do is change pointers. So to take a step back, we're going to do this recursively, which means we're going to have a base case and a recursive case. When do we stop and when do we continue? We want to stop once we hit the end of our linked list, right? So I'm actually going to be making a helper function. I'm going to do def remove node. I'm going to be passing in node and n. So the first thing I'm going to do is my base case. So if node is none, I want to return. So I'm going to return here, but again, I want to keep count of when I am n plus 1 from the end, so I'm going to return some sort of count. At the base case, I'm going to return 0. Now, for my recursive case, what I'm going to do is I'm going to store counts in something called index, and I'm going to call my function again. So self.remove node with my next node, so node.next. This is how we're going to iterate through our linked list. And then at the very end, I'm going to do plus 1. What this means is if I am calling this with a linked list, like in example 1, I would pass in this first node, right? Node is not none, so now I call self.remove node with my next node, n, and then whatever I get from this value, I would add 1 and store that in index. But first, now I need to solve for this value, right? Before I can even add 1. So now I have to call with my own next node, which is 3. And the same thing keeps happening until I hit the very end. Once I hit none, I would return 0. Then I would add 1, and then add 1 as I keep bubbling back up. So once my index is n plus 1, so if index equals n plus 1, I would just change my pointers. So node.next is going to equal node.next.next. Because at this call stack, I am at the node right before the one I want to remove. And all I have to do is return index in the end. Now, I also want to make a call to this helper. So index is going to equal self.remove node with head and n being n. Now, remember that edge case. So if index equals n, what this means is we want to remove that very first node. This is because, say we had the following example, example 1, and n was 5. If index is also 5, this is the node we want to remove because index is keeping track of how far we are from the end, and n is the node we want to remove from the end. If they are equal, we actually want to continue after head. So we are going to return head.next. Otherwise, if that is not the case, all we do is return head because we've already done our pointer changes. So if I go ahead and run this code, it is accepted, and now we can go ahead and submit this. and it is accepted as well. So before leaving, let's actually run through an example to see how everything is going line by line. Okay, so I have the following example with me. I have a linked list with 1, 2, 3, none, and n equals 2, which means this is the node that I want to remove. How would that look like? Well, I go into this function first, and index is going to equal self.remove node of head and 2. So head right now is just going to be node 1. So now I go into the remove node call. I am calling this with node equaling 1 and n equaling 2. Now, going into this function, the first thing I do is make a check if node is none. That is not true. So now I set index equal to this function again. So I'm doing remove node with node being node.next. So what's my next node? That is going to be 2, and n is still 2. And after that, I do plus 1. But before I can do plus 1, I have to solve for this right over here. So remove node with node equaling 2 and n also equaling 2. So I'm back into this function over here, remove node with 2 and 2. If node is none, return 0, it is not none. So now I set index equal to, again, remove node with my next node, n, and then I will add 1 to its output. So remove node with my next node, which is 3, n is 2, and then I will add 1. But before I can add 1, I actually need to get the value of this over here. So remove node with node being 3, n being 2. I go back into this over here, node is not none, so I set index to equal remove node with my next node, which is none, and is still 2, and then I will add 1 to that output. So now when I finally call this function, I am back in here with node being none, and I hit this base case. Node is none, so I am now going to return 0 to my caller. So this is valued at 0, which means I can return up here. This is equal to 0. 0 plus 1 is 1. So index equals 1 at node 3. That means I am now in this if condition. Is index equal to n plus 1? N is 2, and index is 1. That is not true, so I don't go into this if statement, and I return index. So I return 1 to my own caller, which was over here, right? That called node 3, 2, and that's the function call that I am. So I will return 1 to that call over there, and then I can actually solve for that index's value. So 1 plus 1 is 2, and now I am in this if condition. Is index equivalent to n plus 1? N is 2, index is 2. That is not true. Index should have been 3 for that to be equal, which means I don't do anything over here, and I just return index. So I return 2 to my caller. So I return 2 over here. 2 plus 1 is 3. So at node 1, I have index equaling 3. So is index equal to n plus 1? That is true, right? N plus 1 is 3, index is 3, they are equal. So now nodes next is going to be nodes next. I am at node 1, my next value is now going to be my next. So that is going to be 3. There is no 2 anymore. And now I finally return index. So I go ahead and return 3 to my original caller, which was this function over here. And look what happened. We've returned with index being 3, and the linked list now goes from 1 to 3 to none. And now I make a check here. If index equals n, it does not. I would have removed that very first node, so we don't have to do that. And now what I do is I return head. So head is 1, which points to 3, which points to none, and we've successfully removed the second to last node from the end. So this is how to do remove nth node from end of list, both recursively and iteratively, for space and time complexities. Super quickly going over that. For time, because we are just going through our entire linked list, it's going to be dependent on the number of nodes that we have. So that is O of n. And for space, for our recursive approach, that is going to be O of n because we're actually building a call stack that is potentially n nodes high. And for the iterative version, because it's just a one pass and we only have 2 pointers, that is O of 1 for space. So O of n for both time-wise, but O of 1 for the iterative approach and O of n for the recursive approach. If you have any questions whatsoever, Let me know down below. Otherwise, I will see you next time.